let's talk about the seasons. I'm going to be sure to share my screen properly this time so as to not waste time. Okay, so I really like this picture here. Let me get my pen ready to go. Here it is. This is a fun picture. So here's the sun, and if you don't know it's the sun, there, now you know, because the sun is always drawn like this. In this picture, Earth is revolving around the sun. And it takes 365 days for the Earth to revolve once around the sun. To be perfectly honest, it's 365.25 days. And so we only do 365, but every fourth year we add 1 day to make up for the 0.25 times 4. So that's why we have leap year. And leap year is every fourth year on February the 29th, which is our leap day, to make up for the 0.25 that's not considered in our Gregorian calendar. Now, as Earth revolves around the sun, it doesn't make a perfect circle. As a matter of fact, there's a period of time where we're closest to the sun, and that's called perihelion, and there's a period of time where we're furthest from the sun, and that's called aphelion. Perihelion, when we are closest to the sun, that occurs right around January the 3rd. And at this time, we're only about 91 million miles away from the sun. In aphelion, when we are furthest from the sun, that occurs around July the 3rd. And during July the 3rd, we're about 94 million miles away from the sun. So the difference is about 3 million miles. So during aphelion, we're 3 million miles away further from the sun than during perihelion. What's really interesting though in this picture isn't that there's perihelion and aphelion. What's really interesting is that January the 3rd is perihelion and July the 3rd is aphelion. January the 3rd is the heart of winter in the northern hemisphere. And July the 3rd is the heart of summer in the northern hemisphere. How can we be further away from the sun in our summertime and closer to the sun in our wintertime? Clearly, the Earth's proximity to the sun is not the cause of the seasons. Now, before we go any further, if we were in Australia and I was asking the same question, the Australians would say, looks fine to me. Because the fact of the matter is, seasons in the southern hemisphere are opposite to the seasons in our hemisphere. So perihelion, when we are closest to the sun, actually coincides with Australia's summer. And aphelion, when we're furthest from the sun, actually coincides with Australia's winter. But before you say what the heck is going on, you can't have reasons for seasons in one hemisphere being different for seasons in the other hemisphere. So if the shoe doesn't fit both feet, then we need to come up with another solution. So proximity of the Earth to the sun is not the reason why we have the seasons. Something else is. And that's what we need to figure out. So here's some important dates for you to know. The very first day of summer in the northern hemisphere is called the summer solstice. And the summer solstice is right around June 21 to June 22. The very first day of fall in the northern hemisphere is called the autumnal equinox, and that's right around September 21st. The very first day of winter in the northern hemisphere is the winter solstice. That's right around December 21. And the very first day of spring in the northern hemisphere is right around March 21, which is the vernal equinox. Now, summer, fall, winter, and spring are not just singular days out of the year. Each season is going to be approximately 3 months because there's 12 months of the year. But what these dates do indicate are the very first days of these seasons in the northern hemisphere. And the opposite would be true for the summer hemisphere. So what we would really say is this is the June solstice. because the June solstice is the first day of summer in the northern hemisphere and the first day of winter in the southern hemisphere. In addition to that, the summer solstice or the June solstice in the northern hemisphere is the longest day of the year. That doesn't mean that there's more than 24 hours. It just means that the most daylight hours occur on summer solstice. And the shortest day of the year is the winter solstice, where we have the least amount of daylight hours. In the equinoxes, fall or spring, the key word here is equinox or equal, meaning that there's 12 hours of day and 12 hours of night anywhere on the planet during an equinox. Okay, so these are important dates to note. These dates only exist not because of the Earth's distance to the sun, but rather because of the Earth's tilt. The Earth's tilt is the key to the seasons. And so let's draw this picture. So here's the sun. And again, it has to be a smiley face. That's the sun. And we're going to draw this imaginary line coming from the sun. And this imaginary line is called the plane of the ecliptic. So we're going to draw Earth on the plane of the ecliptic because the Earth is revolving around the sun. And it's revolving around the sun, and it resides, again, on the plane of the ecliptic. The Earth is tilted, though, 23.5 degrees relative to the plane of the ecliptic, which means here's the North Pole, and here's the South Pole. And if we're drawing an imaginary line going straight up and down, this angle from the North Pole to the tilt angle is 23.5 degrees. So again, the Earth is tilted 23.5 degrees relative to the plane of the ecliptic. We're going to draw a couple of more lines on this Earth that are important. This line here is the Tropic of Cancer. And the Tropic of Cancer is at 23.5 degrees north latitude. This line of latitude here is going to be the Tropic of Capricorn, and the Tropic of Capricorn is 23.5 degrees south latitude. And that's put in the picture of the equator, which is at 0. I want you to take a really, really close look at this diagram. Listen, I know it's not the greatest. I'm not an artist. I'm trying my best. In this picture, though, I'm going to draw this imaginary line going straight up and down. This is going to be called the circle of illumination, and over here it's nighttime, and over here it's daytime. Okay, so remember the Earth is rotating on its axis, so it's nighttime here, but as the Earth rotates, this area on the equator will eventually get into sunlight, it'll be daytime, etc., etc. I'm going to draw, though, another line of latitude, and this will be the Arctic Circle. And the Arctic Circle is at 66.5 degrees north latitude. And then we draw this line here. This is the Antarctic Circle at 66.5 degrees south latitude. You got to pay really close attention and look at this really closely. The Earth is rotating on its axis. And remember, we're tilted 23.5 degrees. If you're standing anywhere on the Antarctic Circle or below, you are always in nighttime. The sun never rises. It's 24 hours of night. If you're above the Arctic Circle, anywhere above the Arctic Circle, it's 24 hours of day. You never ever rotate into night. If you're standing on the equator, you have 12 hours a day and 12 hours a night. If you're on the equator, you always have 12 hours a day and 12 hours a night. But now take a close look. And again, it's not the best drawing in the world, but it ain't bad. If you're below the equator, you can see that you've got way less hours of daylight versus nighttime. And the higher the latitude you go, or the lower in this case, you get more and more nighttime and less day. Anywhere above the equator, you have way more hours of daylight, going to 24 hours, than you do nighttime. Here in San Diego, California, we're right here above the Tropic of Cancer at around 32 degrees. You'll note that we've got more hours of daylight than we do nighttime. And as a matter of fact, it's like 16 hours to 8. We've got a fair amount of daytime. Now, there's something else I really want you to look at in this picture. And again, this is June 21st. This is the summer solstice. If you're standing right here on the Tropic of Cancer, anywhere on the Tropic of Cancer, and if you go outside at solar noon, you are literally on the plane of the ecliptic, so the sunlight is going to be directly above your head at solar noon. We're talking about Syene. It's like you're standing on Syene. There's no shadow cast at solar noon. But if you're way down here, let's say on the Tropic of Capricorn, notice where your zenith point is. It's here. The sun is over here. It's way angled in the sky. We're going to calculate what that angle is. We'll do it in a second. But you can clearly see that if you're standing on the Tropic of Cancer, not only do you have a relatively long daylight hours, but you also got sunlight that's coming directly down on top of you. This is really important to note. It's this flashlight phenomenon. If you've got sunlight coming straight down on top of you and all this energy is concentrated in a small area relative to sunlight coming in at an angle and not concentrating the solar radiation but spreading it over a longer length, then clearly this is going to be warmer than this because we're just simply concentrating the energy. So in this picture here, not only do we have longer daylight hours, but we're also concentrating the sunlight. It's more direct, which makes it summer conditions. Now, we can look at a half a year later, and let's come way over here to December 21, and this will be the winter solstice, and let's draw the picture again. So now, here's the plane of the ecliptic, and this is the Tropic of Capricorn. Here's the equator. Here's the Tropic of Cancer, North Pole, South Pole, because again, we're tilted 23.5 degrees. Here's the circle of illumination. Here's the Arctic Circle and the Antarctic Circle. This is all nighttime, and this is all daytime. If you are standing here on the Tropic of Capricorn and you go outside at solar noon on December 21, guess what? The sun is directly over your head at solar noon. But now, if you're here at the Tropic of Cancer, take a really close look. This is your zenith point, and your zenith point is at 23.5 degrees. Here's the equator, which is 0 degrees, and here's the sun, which is residing on top of the Tropic of Capricorn at 23.5. So now, 23.5 to 0, 23.5 to 0, that's 50, what is it, 56 degrees, 57 degrees, something like that. That means if you go outside at solar noon and you're standing on the Tropic of Cancer on December 21st, the highest the sun gets in the sky is 57 degrees below your zenith point. It's super low. But when you are here in the summertime, the sun was directly above your head. Literally above your head in the summer. That is a huge difference. And again, we look at the flashlight phenomenon. This is summertime, this is wintertime. But let's also take a look too at the length of daylight hours. Notice how short the daylight hours are now if you're in the Tropic of Cancer and how long the nighttime hours are. Equator is 12 and 12. Tropic of Capricorn is super long daylight hours, not much nighttime. If you're below the Antarctic Circle, it is now 24 hours of day, whereas here it was at 24 hours of night. And if you're above the Arctic Circle, it's now 24 hours of night, when here in the summer it was 24 hours of day. Oh my gosh, this is why we have the seasons. The tilt is not only creating a differential in the amount of daylight hours, but it's also creating a differential in the directness or lack thereof of incoming solar radiation. It's amazing. Let's do an example here. Well, here's the picture. Again, this is the flashlight phenomena. I don't need to go through this. This is sort of a cool image. This is showing the summertime, and you can see how daylight hours change at summer solstice. Arctic Circle and above, 24 hours of daylight. If you're at 40 degrees north latitude, 15 hours of day, which makes it 9 hours of night, because there's 24 hours in a day. If you're on the Tropic of Cancer, 13 and a half hours a day, the rest is night. Equator is 12 and 12. Capricorn is 10 and a half day, the rest is night, which is 13 and a half. 40 degrees south, it's 15 hours of night, 9 hours a day. Below the Antarctic Circle, 24 hours of night, and you can see the slide here for the winter solstice. You can see the slide here for an equinox. During an equinox, it's really fascinating because during an equinox, the tilt is not toward the sun or away from the sun, it's coming out of the page. The tilt is now parallel to the sun. You have to keep in mind that North Celestial Pole star is always above North Geographic Pole, which means that the Earth tilt is not changing as you're revolving around the sun. The Earth's tilt is always staying exactly in the same spot. North Geographic Pole is always directly beneath the North Celestial Pole star. So that means there's a period of time where we're looking at this. This is the equinox. In fact, let's look at the picture here. Here again is summer solstice, and we'll just look at the summer solstice up close. So here's Earth, here's the North Pole, here's the South Pole, here's the equator, Tropic of Cancer, Tropic of Capricorn, Antarctic Circle, Arctic Circle, Circle of Illumination, which is nighttime, daytime. That's summer solstice. If we took a look at the winter solstice, here's the tilt of the Earth, here's the equator, here's the Tropic of Cancer, Tropic of Capricorn, Antarctic Circle, Arctic Circle, Circle of Illumination, daytime, nighttime. It's the exact opposite. And then finally, if we take a look at the equinox, again, it's 12 hours a day, 12 hours a night, everywhere on the planet, because now the tilt is not toward the sun or away from the sun. Now, when I talk about this in class, I like to use this term called solar zenith angle. And I like solar zenith angle because to me it's a little bit more exemplary of what's actually occurring, because now we can figure out where the sun is at in our sky throughout the course of the year. So let's look at San Diego, California in particular, which makes sense because this is where we live, I think, most of us. So here's San Diego, and again, we're at roughly 32 degrees north latitude. The point directly above our head is the zenith, and by the way, if you're just playing Trivial Pursuit, the point directly below you is called the nadir. So this is zenith point, the point directly above our head. Okay, so we've got our sky here. The point directly above our head is 32 degrees north latitude. Now, what's interesting is the following picture. This one. This is where the sun is in our sky throughout the course of the year. So on summer solstice, remember the sun is directly above the Tropic of Cancer at solar noon. Winter solstice, the sun is directly above the Tropic of Capricorn at solar noon. During the equinox, the sun is directly above the equator at solar noon. And remember, that image comes from the following. In fact, let me draw it again. So here's the sun. I'm sorry, I got to do this. Here's the Earth at summer solstice. Equator, Tropic of Cancer. And again, let's draw the plane of the ecliptic. So again, if you're standing here on the Tropic of Cancer, the sun is directly above your head at solar noon. Here, a half a year later, this is the Tropic of Capricorn. Here's the equator. Here's the Tropic of Cancer. If you're standing here on the Tropic of Capricorn, the sun is directly above your head at solar noon. So you see what's happening? The sun is not moving, the earth is just revolving around the sun. Couple that with the earth's tilt, the position of the sun in the sky appears to be changing. We call this solar declination. So during the summer solstice, the solar declination is 23.5 degrees north. During the winter solstice, the solar declination is negative 23.5, or we could say 23.5 degrees south. The equinox is when the earth is right here relative to the sun. Let's draw that picture. So again, here's the sun. And now here's the equinox. Here's the North Pole and the tilt. That's the vernal equinox, and here's the autumnal equinox. Here's the North Pole and the tilt. So again, the tilt in this case is coming out of the page. It's not it's not to or from the sun, it's parallel to it. So now the solar declination is 0 degrees. If you're standing on the equator, the sun is going to be directly over your head at solar noon. And the same is going to be true with the other equinox. Again, the solar declination is 0. So again, throughout the entire year, the sun appears to be moving in the sky, but it really is just the Earth revolution around the sun coupled with the Earth's tilt. So now, let's again look at San Diego. We're again at 32 degrees. So we'll put ourselves in the picture. We know our zenith point is at 32 degrees. We know that during the summer solstice, the first day of summer, the sun, the solar declination, is at 23.5 degrees north. We know it. The sun will never get higher than 23.5. It'll always stay between the tropics, which means that the sun will never, ever, ever be at our zenith point. But during this year, or during this time of year, on June 21, the angle that the sun makes with our zenith point is going to be 32 minus 23.5, which is 8.5 degrees. That means during our summertime, on June 21, the solar zenith angle, I'm going to call it SZA, is 8.5 degrees. That means you go outside at solar noon on June 21, the sun is only 8.5 degrees off of your zenith point. It is almost directly overhead. It's not quite overhead, but it's pretty darn close, which means you're not going to have very long shadows. The sun's going to be pretty direct, and it's going to be pretty toasty, relatively speaking. Now, a quarter of a year later, we segue in from summer to fall, and we hit the autumnal equinox. And so now the sun is going to be down here. It's a bit lower in the sky. This is going to be September 21st, the very first day of fall in the northern hemisphere. And this is where the sun is going to be located. And this is above the equator at 0 degrees. So the solar declination's at 0. That means the angle that the sun makes with us in San Diego is 32 degrees. So if you went outside at September 21 at solar noon, the solar zenith angle is going to equal 32 degrees. That means the sun is 32 degrees below our zenith point. The shadows are getting longer now. We're not at 8.5 anymore, so the shadows are going to get longer and it's going to be a little bit cooler. Now, another quarter of a year goes by, and the sun is getting lower in the sky every single day. And now we hit the winter solstice on December 21, and now the sun is above the Tropic of Capricorn at 23.5 degrees south latitude. So that's where the sun is. That's the highest point in the sky that the sun's going to get for us. So now this angle is 0 to 32, 32 plus 23.5. So 32 plus 23.5 is 55.5 degrees. So on December 21, which is the winter solstice, the solar zenith angle is about 55.5 degrees. That's remarkable. That means in our winter time, the sun is 55.5 degrees from our zenith point. That only puts it like 34.5 degrees above the horizon. That's the highest the sun is going to get throughout the day. Like, it's super low. So the shadows are really, really long. the length of daylight hours we already know is shortened because of the picture I showed you regarding the changing position of the circle of illumination. So that makes it wintertime. It's going to be colder. The sun isn't as high in the sky, so we have that flashlight phenomena, and the length of daylight hours is shortened. Okay, now a quarter of a year goes by, and we're moving back on up. We're going to hit an equinox again. And now this case is going to be the March equinox, or the vernal equinox, which is March 21. And on March 21, once again, the sun is above zero. So on March 21, the very first day of spring in the northern hemisphere, the solar zenith angle once again is 32 degrees. And then a quarter of a year goes by, we find ourselves in summer, and once again, we're back to start 8.5 degrees. That is the path of the seasons for us in San Diego. Now, you may ask yourself the following question. Let's say that we draw a picture of North America. It's not a very good picture, I understand. I've neglected Texas, I believe. Here's the Gulf of California. That's good enough. Here's us at 32. And here's our counterpart at 32. And in fact, we can even put Tucson here, Tucson, Arizona, at about 32. Have you been to Tucson, Arizona? In the summertime, it's super hot. It's easily over 100 degrees Fahrenheit on the daily. They're at the same latitude, which means that their solar radiation, their solar zenith angle is the same as ours. But in their wintertime, it's super cold. We're talking like 40 degrees. Our wintertime is the high 60s. Our summertime is typically the high 80s, if that. So clearly, there's other things at play, which is going to create temperature differential across the planet. We can easily see that the biggest reason for that is we live on the Pacific Ocean and Tucson is inland. In addition to that, some serious winds blow from the Gulf of Mexico, and it creates what's called a monsoonal tendency, and it brings a fair amount of humidity here for our friends in Arizona. But nevertheless, with all that said, the biggest key to temperature variations across the planet is going to be seasonal. And seasonal is based on the seasons, and it's based on this picture right here. The changing angle of the sun throughout the course of the year, coupled with the changing length of daylight hours throughout the course of the year. Okay? That's the seasons.